Hi, everyone. Welcome to CS25 Transformers United video. This was a course that was held at Stanford in the winter of 2023. This course is not about robots that can transform into cars, as this picture might suggest. Rather, it's about deep learning models that have taken the world by the storm and have revolutionized the field of AI and others. Starting from natural language processing, transformers have been applied all over, from computer vision, reinforcement learning, biology, robotics, etc. We have an exciting set of videos lined up for you, with some truly fascinating speakers give talks presenting how they're applying transformers to the research in different fields and areas. We hope you'll enjoy and learn from these videos. So without any further ado, let's get started. This is a purely introductory lecture, and we'll go into the building blocks of transformers. So first, let's start with introducing the instructors.
So for me, I'm currently on a temporary deferral from the PhD program, and I'm leading AI at a robotics startup, Collaborative Robotics, where we're working on some general purpose robots, somewhat like a robot. And yeah, I'm very passionate about robotics and building efficient learning algorithms. My research interests are in reinforcement learning, computer vision, generative modeling, and I have a bunch of publications in robotics, autonomous driving, and other areas. My undergrad was at Cornell. It's someone spoke Cornell. So nice to meet you.
So I'm Steven, currently first year CSP speaker. Previously did my master's at CMU and undergrad at Waterloo. Mainly into NLP research, anything involving language and text. But more recently, I've been getting more into computer vision as well as multimodal. And just some stuff I do for fun. A lot of music stuff, mainly piano. Some self-promo, but I post a lot on my Insta, YouTube, and TikTok. So if you guys want to check it out. My friends and I are also starting a Stanford piano club. So if anybody's interested, feel free to email or DM me for details. Other than that, martial arts, bodybuilding, and huge fan of K-dramas, anime, and occasional gamer.
Okay, cool. Yeah, so my name's Rylan. Instead of talking about myself, I just want to very briefly say that I'm super excited to take this class. I took it the last time it was offered. Sorry, to teach this class. Excuse me. I took it the last time it was offered. I had a bunch of fun. I thought we brought in a really great group of speakers last time. I'm super excited for this offering. And yeah, I'm thankful you're all here, and I'm looking forward to a really fun quarter together. Thank you.
Yeah, so fun fact, Rylan was the most outspoken student last year. And so if someone wants to become an instructor next year, you know what to do. Okay, cool. Let's see. Okay, we have a few minutes. So what we hope you will learn in this class is, first of all, how do transformers work, how they're being applied, just beyond NLP. And nowadays, like, we are pretty much using them everywhere in AI, machine learning. And what are some new interesting directions of research in these topics? Cool. So this class is just an introductory. So we're just talking about the basics of transformers, introducing them, talking about the self-attention mechanism on which they're founded. And we'll do a deep dive more on like models like BERT, GPT, stuff like that. So great, happy to get started. Okay, so let me start with presenting the attention timeline. Attention all started with this one paper, Attention is All You Need, by Vaswani et al. In 2017. That was the beginning of transformers. Before that, we had the prehistoric era, where we had models like RNNs, LSTMs, and simple attention mechanisms that didn't work or scale that well. Starting 2017, we saw this explosion of transformers into NLP, where people started using it for everything. I even heard this quote from Google. It's like, our performance increased every time we fired our linguist. So that was 2018. After 2018 to 2020, we saw this explosion of transformers into other fields like vision, bunch of other stuff, and like biology, AlphaFold. And in last year, 2021 was the start of the generative era, where we got like a lot of generative modeling. Started like models like Codex, GPT, DALI, Stable Diffusion. So a lot of like things happening in generative modeling, and so we started scaling up in AI. And now it's the present. So this is 2022 and like the start of 2023. And now we have models like ChatGPT, Whisper, a bunch of others. And we are like scaling onwards without slowing down. So that's great. So that's the future. So going more into this, so once there were RNNs, So we had sequence-to-sequence models, LSTMs, GIUs. What worked here was that they were good at encoding history, but what did not work was they didn't encode long sequences, and they were very bad at encoding context. So consider this example. Consider trying to predict the last word in the text, I grew up in France, ... I speak fluent dash. Here, you need to understand the context for it to predict French, and like attention mechanism is very good at that. Whereas if you're just using LSTMs, it doesn't work that well. Another thing transformers are good at is more based on content is also context prediction is like finding attention maps. If I have something like a word like it, what noun does it correlate to? And we can give like a probability attention on what are the possible activations. And this works better than existing mechanisms. Okay. So where we were in 2021, we were on the verge of takeoff. We were starting to realize the potential of transformers in different fields. We solved a lot of long sequence problems like protein folding, AlphaFold, offline RL. We started to see zero-shot generalization. We saw multimodal tasks and applications like generating images from language. So that was DALI. Yeah, and it feels like Asian, but it was only like 2 years ago. And this is also a talk on transformers that you can watch on YouTube. Yeah, cool. And this is where we were going from 2021 to 2022, which is we have gone from the verge of taking off to actually taking off. And now we are seeing unique applications in audio generation, art, music, storytelling. We are starting to see reasoning capabilities like common sense, logical reasoning, mathematical reasoning. We are also able to now get human enlightenment and interaction. They're able to use reinforcement learning and human feedback. That's how ChatGPT is trained to perform really good. We have a lot of mechanisms for controlling toxicity, bias, and ethics now, and a lot of developments in other areas like diffusion models. Cool. So the future is a spaceship, and we are all excited about it. And there's a lot of more applications that we can enable. And it'll be great if you can see transformers also work there. One big example is video understanding and generation. That is something that everyone is interested in. And I'm hoping we'll see a lot of models in this area this year. Also finance, business. I'll be very excited to see GPT author a novel, but we need to solve very long sequence modeling. And most transformer models are still limited to like 4,000 tokens or something like that. So we need to do make them generalize much more better on long sequences. We also want to have generalized agents that can do a lot of multitask, multi-input predictions like Gato. And so I think we will see more of that too. And finally, we also want domain-specific models. So you might want like a GPT model that's good at like maybe like health. So that could be like a doctor GPT model. You might have like a law GPT model that's like trained on only on law data. So currently we have like GPT models that are trained on everything, but we might start to see more niche models that are like good at one task. And we could have like a mixture of experts. So it's like you can think like this is like how you normally consult an expert. You'll have like expert AI models, and you can go to a different AI model for your different needs. There are still a lot of missing ingredients to make this all successful. The first of all is external memory. We are already starting to see this with models like ChatGPT, where the interactions are short-lived. There's no long-term memory, and they don't have ability to remember or store conversations for long-term. And this is something we want to fix. Second is reducing the computation complexity. So attention mechanism is quadratic over the sequence length, which is slow, and we want to reduce it or make it faster. Another thing we want to do is we want to enhance the controllability of these models. Like a lot of these models can be stochastic, and we want to be able to control what sort of outputs we get from them. And you might have experienced with ChatGPT. If you just refresh, you get like different output each time, but you might want to have a mechanism that controls what sort of things you get. And finally, we want to align our state-of-art language models with how the human brain works. And we are seeing research, but we still need more research on seeing how they can be made more informed. Great, thank you.
Great, hi. Yes, I'm excited to be here. I live very nearby, so I got the invites to come to class, and I was like, okay, I'll just walk over. But then I spent like 10 hours on the slides, so it wasn't as simple. So yeah, I want to talk about transformers. I'm going to skip the first two over there. We're not going to talk about those. We're going to talk about that one, just to simplify the lecture since we don't have time. Okay, so I wanted to provide a little bit of context of why does this transformers class even exist. So a little bit of historical context. I feel like Bilbo over there. I joined like telling you guys about this. I don't know if you guys saw Lord of the Rings. And basically, I joined AI in roughly 2012 in full force, so maybe a decade ago. And back then, you wouldn't even say that you joined AI, by the way. That was like a dirty word. Now it's okay to talk about, but back then, it was not even deep learning. It was machine learning. That was a term you would use if you were serious. But now AI is okay to use, I think. So basically, do you even realize how lucky you are potentially entering this area in roughly 2023? So back then, in 2011 or so, when I was working specifically on computer vision, your pipelines looked like this. So you wanted to classify some images. You would go to a paper, and I think this is representative. You would have 3 pages in the paper describing all kinds of a zoo of kitchen sink of different kinds of features, descriptors. And you would go to a poster session and in computer vision conference, and everyone would have their favorite feature descriptor that they're proposing, and it was totally ridiculous. And you would take notes on like which one you should incorporate into your pipeline, because you would extract all of them, and then you would put an SVM on top. So that's what you would do. So there's 2 pages. Make sure you get your sparse SIP histograms, your SSIMs, your color histograms, text dons, tiny images, and don't forget the geometry-specific histograms. All of them had basically complicated code by themselves. So you're collecting code from everywhere and running it, and it was a total nightmare. On top of that, it also didn't work. So this would be, I think, representative prediction from that time. You would just get predictions like this once in a while, and you'd be like, you just shrug your shoulders like that just happens once in a while. Today, you would be looking for a bug. And worse than that, every single sort of field of every single chunk of AI had their own completely separate vocabulary that they work with. So if you go to NLP papers, those papers would be completely different. So you're reading the NLP paper, and you're like, what is this part of speech tagging, morphological analysis, syntactic parsing, co-reference resolution? What is NP, BT, JJ? And you're confused. So the vocabulary and everything was completely different, and you couldn't read papers, I would say, across different areas. So now that changed a little bit starting 2012 when Alex Kuchevsky and colleagues basically demonstrated that if you scale a large neural network on large data set, you can get very strong performance. And so up till then, there was a lot of focus on algorithms, but this showed that actually neural nets scale very well. So you need to now worry about compute and data, and if you scale it up, it works pretty well. And then that recipe actually did copy paste across many areas of AI. So we started to see neural networks pop up everywhere since 2012. So we saw them in computer vision and NLP and speech and translation in RL and so on. So everyone started to use the same kind of modeling toolkit, modeling framework. And now when you go to NLP and you start reading papers there in machine translation, for example, this is a sequence-to-sequence paper, which we'll come back to in a bit. You start to read those papers and you're like, okay, I can recognize these words, like there's a neural network, there's some parameters, there's an optimizer, and it starts to read like things that you know of. So that decreased tremendously the barrier to entry across the different areas. And then I think the big deal is that when the transformer came out in 2017, it's not even that just the toolkits and the neural networks were similar, it's that literally the architectures converged to like one architecture that you copy paste across everything seemingly. So this was kind of an unassuming machine translation paper at the time proposing the transformer architecture. But what we found since then is that you can just basically copy paste this architecture and use it everywhere. And what's changing is the details of the data and the chunking of the data and how you feed it in. And that's a caricature, but it's kind of like a correct first order statement. And so now papers are even more similar looking because everyone's just using transformer. And so this convergence was remarkable to watch and unfolded over the last decade, and it's pretty crazy to me. What I find kind of interesting is I think this is some kind of a hint that we're maybe converging to something that maybe the brain is doing, because the brain is very homogeneous and uniform across the entire sheet of your cortex. And okay, maybe some of the details are changing, but those feel like hyperparameters of like a transformer. But your auditory cortex and your visual cortex and everything else looks very similar. And so maybe we're converging to some kind of a uniform, powerful learning algorithm here something like that, I think is kind of interesting and exciting. Okay, so I want to talk about where the transformer came from briefly, historically. So I want to start in 2003. I like this paper quite a bit. It was the first sort of popular application of neural networks to the problem of language modeling. So predicting, in this case, the next word in a sequence, which allows you to build generative models over text. And in this case, they were using multi-layer perceptron. So a very simple neural net. The neural net took 3 words and predicted the probability distribution for the 4th word in a sequence. So this was well and good at this point. Now, over time, people started to apply this to machine translation. So that brings us to sequence paper from 2014 that was pretty influential. And the big problem here was, okay, we don't just want to take 3 words and predict the 4th. We want to predict how to go from an English sentence to a French sentence. And the key problem was, okay, you can have arbitrary number of words in English and arbitrary number of words in French. So how do you get an architecture that can process this variably sized input? And so here they used a LSTM, and there's basically 2 chunks of this, which are covered by the by this. But basically you have an encoder LSTM on the left, and it just consumes one word at a time and builds up a context of what it has read. And then that acts as a conditioning vector to the decoder RNN or LSTM that basically goes chunk for the next word in the sequence, translating the English to French or something like that. Now, the big problem with this that people identified, I think, very quickly and tried to resolve is that there's what's called this encoder bottleneck. So this entire English sentence that we are trying to condition on is packed into a single vector that goes from the encoder to the decoder. And so this is just too much information to potentially maintain in a single vector, and that didn't seem correct. And so people were looking around for ways to alleviate the encoder bottleneck, as it was called at the time. And so that brings us to this paper, Neural Machine Translation by Jointly Learning to Align and Translate. And here, just quoting from the abstract, in this paper, we conjectured that the use of a fixed length vector is a bottleneck in improving the performance of the basic encoder-decoder architecture, and proposed to extend this by allowing the model to automatically soft search for parts of the source sentence that are relevant to predicting a target word, without having to form these parts or hard segments explicitly. So this was a way to look back to the words that are coming from the encoder. And it was achieved using this soft search. So as you are decoding in the words here, while you are decoding them, you are allowed to look back at the words at the encoder via this soft attention mechanism proposed in this paper. And so this paper, I think, is the first time that I saw basically attention. So your context vector that comes from the encoder is a weighted sum of the hidden states of the words in the encoding. And then the weights of this sum come from a softmax that is based on these compatibilities between the current state as you're decoding and the hidden states generated by the encoder. And so this is the first time that really you start to look at it, and this is the current modern equations of the attention. And I think this was the first paper that I saw it in. It's the first time that there's word attention used, as far as I know, to call this mechanism. So I actually tried to dig into the details of the history of the attention. So the first author here, Dmitry, I had an email correspondence with him, and I basically sent him an email. I'm like, Dmitry, this is really interesting. Transformers have taken over. Where did you come up with the soft attention mechanism that ends up being the heart of the transformer? And to my surprise, he wrote me back this massive email, which was really fascinating. So this is an excerpt from that email. So basically, he talks about how he was looking for a way to avoid this bottleneck between the encoder and decoder. He had some ideas about cursors that traversed the sequences that didn't quite work out. And then here, so one day I had this thought that it would be nice to enable the decoder RNN to learn to search where to put the cursor in the source sequence. This was sort of inspired by translation exercises that learning English in my middle school involved. You gaze shifts back and forth between source and target sequence as you translate. So literally, I thought this was kind of interesting that he's not a native English speaker. And here that gave him an edge in this machine translation that led to attention and then led to transformer. So that's really fascinating. I expressed the soft search as softmax and then weighted averaging of the binary states. And basically, to my great excitement, this worked from the very first try. So really, I think, interesting piece of history. And as it later turned out, the name of RNN search was kind of lame. So the better name, attention, came from Joshua on one of the final passes as they went over the paper. So maybe attention is all you need would have been called RNN search is all you need. But we have Joshua Bengio to thank for little bit of better name, I would say. So apparently that's the history of this, which I thought was interesting. Okay, so that brings us to 2017, which is attention is all you need. So this attention component, which in Dimitri's paper was just like one small segment, and there's all this bidirectional RNN and decoder, and this attention all you need paper is saying, okay, you can actually delete everything. Like what's making this work very well is just the attention by itself. And so delete everything, keep attention. And then what's remarkable about this paper actually is usually you see papers that are very incremental. They add like one thing and they show that it's better. But I feel like attention is all you need was like a mix of multiple things at the same time. They were combined in a very unique way, and then also achieved a very good local minimum in the architecture space. And so to me, this is really a landmark paper that is quite remarkable, and I think had quite a lot of work behind the scenes. So delete all the RNN, just keep attention. Because attention operates over sets, and I'm going to go into this in a second, you now need to positionally encode your inputs because attention doesn't have the notion of space by itself. Oops, I have to be very careful. They adopted this residual network structure from ResNets. They interspersed attention with multi-layer perceptrons. They used layer norms, which came from a different paper. They introduced the concept of multiple heads of attention that were applied in parallel. And they gave us, I think, like a fairly good set of hyperparameters that to this day are used. So the expansion factor in the multi-layer perceptron goes up by 4x, and we'll go into like a bit more detail. And this 4x has stuck around. And I believe like there's a number of papers that try to play with all kinds of little details of the transformer, and nothing like sticks because this is actually quite good. The only thing to my knowledge that stuck, that didn't stick, was this reshuffling of the layer norms to go into the pre-norm version, where here you see the layer norms are after the multi-headed attention or feed-forward. They just put them before instead. So just reshuffling of layer norms, but otherwise the GPTs and everything else that you're seeing today is basically the 2017 architecture from 5 years ago. And even though everyone is working on it, it's proven remarkably resilient, which I think is really interesting. There are innovations that I think have been adopted also in positional encodings. It's more common to use different rotary and relative positional encodings and so on. So I think there have been changes, but for the most part, it's proven very resilient. So really quite an interesting paper. Now, I wanted to go into the attention mechanism. And I think I sort of like the way I interpret it is not similar to the ways that I've seen it presented before. So let me try a different way of like how I see it. Basically, to me, attention is kind of like the communication phase of the transformer. And the transformer interleaves two phases. The communication phase, which is the multi-headed attention, and the computation stage, which is this multi-layer perceptron or feed-forward. So in the communication phase, it's really just a data-dependent message passing on directed graphs. And you can think of it as, okay, forget everything with machine translation and everything. We have directed graphs at each node. You are storing a vector. And then let me talk now about the communication phase of how these vectors talk to each other in this directed graph. And then the compute phase later is just the multi-layer perceptron, which then basically acts on every node individually. But how do these nodes talk to each other in this directed graph? So I wrote like some simple Python, I wrote this in Python basically to create one round of communication of using attention as the message passing scheme. So here, a node has this private data vector, as you can think of it as private information to this node. And then it can also emit a key, a query, and a value. And simply that's done by linear transformation from this node. So the key is what are the things that I am, the query is what are the things that I'm looking for. The key is what are the things that I have. And the value is what are the things that I will communicate. And so then when you have your graph that's made up of nodes and some random edges, when you actually have these nodes communicating, what's happening is you loop over all the nodes individually in some random order, and you're at some node, and you get the query vector Q, which is I'm a node in some graph, and this is what I'm looking for. And so that's just achieved via this linear transformation here. And then we look at all the inputs that point to this node, and then they broadcast what are the things that I have, which is their keys. So they broadcast the keys. I have the query. Then those interact by dot product to get scores. So basically, simply by doing dot product, you get some kind of a unnormalized weighting of the interestingness of all of the information in my in the nodes that point to me and to the things I'm looking for. And then when you normalize that with a softmax, so it just sums to 1, you basically just end up using those scores, which now sum to 1 in our probability distribution, and you do a weighted sum of the values to get your update. So I have a query, they have keys, dot product to get interestingness or like affinity, softmax to normalize it, and then weighted sum of those values flow to me and update me. And this is happening for each node individually, and then we update at the end. And so this kind of a message passing scheme is kind of like at the heart of the transformer, and happens in a more vectorized, batched way that is more confusing, and is also interspersed with layer norms and things like that to make the training behave better. But that's roughly what's happening in the attention mechanism, I think, on a high level. So yeah, so in the communication phase of the transformer, then this message passing scheme happens in every head in parallel, and then in every layer in series, and with different weights each time. And that's it as far as the multi-headed attention goes. And so if you look at these encoder-decoder models, you can sort of think of it then in terms of the connectivity of these nodes in the graph. You can kind of think of it as like, okay, all these tokens that are in the encoder that we want to condition on, they are fully connected to each other. So when they communicate fully when you calculate their features. But in the decoder, because we are trying to have a language model, we don't want to have communication from future tokens because they give away the answer at this step. So the tokens in the decoder are fully connected from all the encoder states, and then they are also fully connected from everything that is before them. And so you end up with this like triangular structure in the directed graph. But that's the message passing scheme that this basically implements. And then you have to be also a little bit careful because in the cross attention here with the decoder, you consume the features from the top of the encoder. So think of it as in the encoder, all the nodes are looking at each other, all the tokens are looking at each other many, many times, and they really figure out what's in there. And then the decoder, when it's looking only at the top nodes. So that's roughly the message passing scheme. I was going to go into more of an implementation of the transformer. I don't know if there's any questions about this scheme.
Explain a little bit of this self-attention and multi-headed attention, but what is the advantage of that?
Yeah, so self-attention and multi-headed attention. So the multi-headed attention is just this attention scheme, but it's just applied multiple times in parallel. Multiple heads just means independent applications of the same attention. So this message passing scheme basically just happens in parallel multiple times with different weights for the query key and value. So you can almost look at it like in parallel, I'm seeking different kinds of information from different nodes, and I'm collecting it all in the same node. It's all done in parallel. So heads is really just like copy paste in parallel, and layers are copy paste but in series. Maybe that makes sense. And self-attention, when it's self-attention, what it's referring to is that the node here produces each node here. So as I described it here, this is really self-attention because every one of these nodes produces a key query and a value from this individual node. When you have cross-attention, you have one cross-attention here coming from the encoder. That just means that the queries are still produced from this node, but the keys and the values are produced as a function of nodes that are coming from the encoder. So I have my queries because I'm trying to decode the fifth word in the sequence, and I'm looking for certain things because I'm the fifth word. And then the keys and the values in terms of the source of information that could answer my queries can come from the previous nodes in the current decoding sequence or from the top of the encoder. So all the nodes that have already seen all of the encoding tokens many, many times can now broadcast what they contain in terms of information. So I guess to summarize, the self-attention is kind of like, cross-attention and self-attention only differ in where the keys and the values come from. Either the keys and values are produced from this node, or they are produced from some external source like an encoder and the nodes over there. But algorithmically is the same mathematical operations.
Question.
Okay.
So the two questions. The first question is, in the message passing graph paradigm, what were the layers that were put together?
So yeah, so think of so each one of these nodes is a token. I guess like they don't have a very good picture of it in the transformer, but like this node here could represent the third word in the output in the decoder, and in the beginning it is just the embedding of the word. And then, okay, I have to think through this analogy a little bit more. I came up with it this morning. Actually, I came up with it yesterday.
We have another question. What example of instantiation is a good instantiation test? Nodes as in blocks, word embedding?
These nodes are basically the vectors. I'll go to an implementation. I'll go to the implementation, and then maybe I'll make the connections to the graph. So let me try to first let me now go to, with this intuition in mind at least, to NanoGPT, which is a concrete implementation of a transformer that is very minimal. So I worked on this over the last few days, and here it is reproducing GPT-2 on open web text. So it's a pretty serious implementation that reproduces GPT-2, I would say, and provided enough compute. This was one node of 8 GPUs for 38 hours or something like that, if I remember correctly. And it's very readable. It's 300 lines, so everyone can take a look at it. Yeah, let me basically briefly step through it. So let's try to have a decoder-only transformer. So what that means is that it's a language model. It tries to model the next word in the sequence or the next character in the sequence. So the data that we train on is always some kind of text. So here's some fake Shakespeare. Sorry, this is real Shakespeare. We're going to produce fake Shakespeare. So this is called the tiny Shakespeare dataset, which is one of my favorite toy datasets. You take all of Shakespeare, concatenate it, and it's 1 megabyte file, and then you can train language models on it and get infinite Shakespeare if you like, which I think is kind of cool. So we have a text. The first thing we need to do is we need to convert it to a sequence of integers, because transformers natively process, you can't plug text into transformer. You need to somehow encode it. So the way that encoding is done is we convert, for example, in the simplest case, every character gets an integer. And then instead of hi there, we would have this sequence of integers. So then you can encode every single character as an integer and get like a massive sequence of integers. You just concatenate it all into one large, long, one-dimensional sequence, and then you can train on it. Now here we only have a single document. In some cases, if you have multiple independent documents, what people like to do is create special tokens, and they intersperse those documents with those special end-of-text tokens that they splice in between to create boundaries. But those boundaries actually don't have any modeling impact. It's just that the transformer is supposed to learn via backpropagation that the end of document sequence means that you should wipe the memory. Okay, so then we produce batches. So these batches of data just mean that we go back to the one-dimensional sequence and we take out chunks of this sequence. So say if the block size is 8, then the block size indicates the maximum length of context that your transformer will process. So if our block size is 8, that means that we are going to have up to 8 characters of context to predict the 9th character in the sequence. And the batch size indicates how many sequences in parallel we're going to process. And we want this to be as large as possible, so we're fully taking advantage of the GPU and the parallels on the boards. So in this example, we're doing 4x8 batches. So every row here is independent example, sort of. And then every row here is a small chunk of the sequence that we're going to train on. And then we have both the inputs and the targets at every single point here. So to fully spell out what's contained in a single 4x8 batch to the transformer, I sort of like unpacked it here. So when the input is 47 by itself, the target is 58. And when the input is the sequence 4758, the target is 1. And when it's 4758-1, the target is 51, and so on. So actually, the single batch of examples, that's 4x8, actually has a ton of individual examples that we are expecting the transformer to learn on in parallel. And so you'll see that the batches are learned on completely independently, but the time dimension sort of here along horizontally is also trained on in parallel. So sort of your real batch size is more like b times t. It's just that the context grows linearly for the predictions that you make along the t direction in the model. So this is how this is all the examples that the model will learn from this single batch. So now this is the GPT class, and because this is a decoder-only model, so we're not going to have an encoder because there's no like English we're translating from we're not trying to condition on some other external information. We're just trying to produce a sequence of words that follow each other or are likely to. So this is all PyTorch, and I'm going slightly faster because I'm assuming people have taken 231 or something along those lines. But here in the forward pass, we take these indices, and then we both encode the identity of the indices just via an embedding lookup table. So every single integer has we index into a lookup table of vectors in this nn.embedding and pull out the word vector for that token. And then because transform by itself doesn't actually, it processes sets natively. So we need to also positionally encode these vectors so that we basically have both the information about the token identity and its place in the sequence from 1 to block size. Now, the information about what and where is combined additively. So the token embeddings and the positional embeddings are just added exactly as here. So this X here, then there's optional dropout. This X here basically just contains the set of words and their positions. And that feeds into the blocks of transformer. And we're going to look into what's block here. But for now, this is just a series of blocks in the transformer. And then in the end, there's a layer norm. And then you're decoding the logits for the next word or next integer in the sequence using a linear projection of the output of this transformer. So LM head here, short for language model head, is just a linear function. So basically, positionally encode all the words, feed them into a sequence of blocks, and then apply a linear layer to get the probability distribution for the next character. And then if we have the targets, which we produced in the data loader, and you'll notice that the targets are just the inputs offset by 1 in time, then those targets feed into a cross entropy loss. So this is just a -1 likelihood typical classification loss. So now let's drill into what's here in the blocks. So these blocks that are applied sequentially, there's again, as I mentioned, this communicate phase and the compute phase. So in the communicate phase, all the nodes get to talk to each other. And so these nodes are basically, if our block size is 8, then we are going to have 8 nodes in this graph. There's 8 nodes in this graph. The first node is pointed to only by itself. The second node is pointed to by the first node and itself. The third node is pointed to by the first 2 nodes and itself, etc. So there's 8 nodes here. So you apply, there's a residual pathway in X. You take it out, you apply a layer norm, and then the self-attention so that these communicate, these 8 nodes communicate. But you have to keep in mind that the batch is 4. So because batch is 4, this is also applied. So we have 8 nodes communicating, but there's a batch of 4 of them all individually communicating among those 8 nodes. There's no crisscross across the batch dimension, of course. There's no batch norm layers anywhere, luckily. And then once they've changed information, they are processed using the multi-layer perceptron, and that's the compute phase. So, and then also here we are missing the cross attention, because this is a decoder-only model. So all we have is this step here, the multi-headed retention, and that's this line, the communicate phase. And then we have the feed forward, which is the MLP, and that's the compute phase. I'll take questions a bit later. Then the MLP here is fairly straightforward. The MLP is just individual processing on each node, just transforming the feature representation sort of at that node. So applying a 2-layer neural net with a GALU nonlinearity, which is, just think of it as a ReLU or something like that. It's just a nonlinearity. And then MLP is straightforward. I don't think there's anything too crazy there. And then this is the causal self-attention part, the communication phase. So this is kind of like the meat of things and the most complicated part. It's only complicated because of the batching and the implementation detail of how you mask the connectivity in the graph so that you can't obtain any information from the future when you're predicting your token. Otherwise, it gives away the information. So if I'm the 5th token, and if I'm the 5th position, then I'm getting the 4th token coming into the input, and I'm attending to the 3rd, 2nd, and 1st, and I'm trying to figure out what is the next token. Well, then in this batch, in the next element over in the time dimension, the answer is at the input. So I can't get any information from there. So that's why this is all tricky. But basically in the forward pass, we are calculating the queries, keys, and values based on X. So these are the keys, queries, and values. Here, when I'm computing the attention, I have the queries matrix multiplying the keys. So this is the dot product in parallel for all the queries and all the keys in all the heads. So that I failed to mention that there's also the aspect of the heads, which is also done all in parallel here. So we have the batch dimension, the time dimension, and the head dimension, and you end up with 5-dimensional tensors, and it's all really confusing. So I invite you to step through it later and convince yourself that this is actually doing the right thing. But basically, you have the batch dimension, the head dimension, and the time dimension, and then you have features at them. And so this is evaluating for all the batch elements, for all the head elements, and all the time elements, the simple Python that I gave you earlier, which is query.product t. Then here we do a masked fill. And what this is doing is it's basically clamping the attention between the nodes that are not supposed to communicate to be negative infinity. And we're doing negative infinity because we're about to softmax. And so negative infinity will make basically the attention at those elements be 0. And so here we are going to basically end up with the weights, the sort of affinities between these nodes, optional dropout, and then here attention matrix multiply V is basically the gathering of the information according to the affinities we've calculated. And this is just a weighted sum of the values at all those nodes. So this matrix multiply is doing that weighted sum. And then transpose contiguous view, because it's all complicated and batched in 5-dimensional tensors, but it's really not doing anything. Optional dropout, and then a linear projection back to the residual pathway. So this is implementing the communication phase here. Then you can train this transformer, and then you can generate infinite Shakespeare, and you will simply do this by, because our block size is 8, we start with a sum token. Say like I used, in this case, you can use something like a new line as the start token. And then you communicate only to yourself because there's a single node, and you get the probability distribution for the first word in the sequence. And then you decode it, or the first character in the sequence, you decode the character, and then you bring back the character and you re-encode it as an integer. And now you have the second thing. And so you get, okay, we're at the first position, and this is whatever integer it is. Add the positional encodings, goes into the sequence, goes into transformer. And again, this token now communicates with the first token and its identity. And so you just keep like plugging it back. And once you run out of the block size, which is 8, you start to crop, because you can never have block size more than 8 in the way we've trained this transformer. So we have more and more context until 8. And then if you want to generate beyond 8, you have to start cropping, because the transformer only works for 8 elements in time dimension. And so all of these transformers in the naive setting have a finite block size or context length. And in typical models, this will be 1024 tokens or 2048 tokens, something like that. But these tokens are usually like DPE tokens or sentence piece tokens or word piece tokens. There's many different encodings. So it's not like that long. And so that's why I think Dib mentioned we really want to expand the context size, and it gets gnarly because the attention is quadratic in the naive case. Now, if you want to implement an encoder instead of a decoder attention, then all you have to do is this mask code, you just delete that line. So if you don't mask the attention, then all the nodes communicate to each other, and everything is allowed, and information flows between all the nodes. So if you want to have the encoder here, just delete all the encoder blocks will use attention where this line is deleted. That's it. So you're allowing whatever this encoder might store, say 10 tokens, like 10 nodes, and they are all allowed to communicate to each other going up the transformer. And then if you want to implement cross attention, so you have a full encoder decoder transformer, not just a decoder only transformer or GPT, then we need to also add cross attention in the middle. So here there's a self attention piece where there's a self attention piece, a cross attention piece, and this MLP. And in the cross attention, we need to take the features from the top of the encoder. We need to add one more line here, and this would be the cross attention instead of I should have implemented it instead of just pointing, I think. But there will be a cross attention line here, so we'll have 3 lines because we need to add another block. And the queries will come from X, but the keys and the values will come from the top of the encoder. And there will be basically information flowing from the encoder strictly to all the nodes inside X. And then that's it. So it's very simple sort of modifications on the decoder attention. So you'll hear people talk that you kind of have a decoder only model like GPT. You can have an encoder only model like BERT, or you can have an encoder decoder model like say T5 doing things like machine translation. So, and in BERT, you can't train it using sort of this language modeling setup that's autoregressive, and you're just trying to predict the next element in the sequence. You're training it with slightly different objectives. You're putting in like the full sentence, and the full sentence is allowed to communicate fully. And then you're trying to classify sentiment or something like that. So you're not trying to model like the next token in the sequence. So these are trained slightly different with masked, using masking and other denoising techniques. Okay, so that's kind of like the transformer. I'm going to continue. So yeah, maybe more questions.
Can you go back to so when we were importing information, we connected graph to remote it and when we were like coding the tag, this transfer will still perform like it's a dynamic graph that the connection change in every instant, and we also have some feature information for the same thing. So it's just like we are enforcing these constraints on it by just masking, but is it aware of their work and things?
So I'm not sure if I fully follow. So there's different ways to look at this analogy, but one analogy is you can interpret this graph as really fixed. It's just that every time we do the communicate, we are using different weights. You can look at it that way. So if we have block size of 8 in my example, we would have 8 nodes. Here we have 2, 4, 6. Okay, so we'd have 8 nodes. They would be connected in you lay them out and you only connect from left to right.
I mean, but for different problems, that might not be different. You actually have a graph where the connections might change.
Why would the usually the connections don't change as a function of the data or something like that.
I mean, like the molecule, like an actual graph, like the management molecule, they want to apply this. It's not just NLP. I'm wondering if like there's any.
I don't think I've seen a single example where the connectivity changes dynamically as a function of data. Usually the connectivity is fixed. If you have an encoder and you're training a BERT, you have how many tokens you want and they are fully connected. And if you have decoder only model, you have this triangular thing. And if you have encoder decoder, then you have awkwardly sort of like 2 pools of nodes. Yeah. Go ahead.
I guess there's I think if there's like a like a negative speed, the calculation. So like it's like my question is I wonder if you know much more about this than I know actually. But like do you have a sense of like, if you ran like a population study which parts of the result. Like in my head, I'm thinking of the visual connection and also have but then you also have like different things like very similar norm and
yeah, it's really hard to say. So that's why I think this paper is so interesting is like, yeah, usually you'd see like a path and maybe they had path internally, they just didn't publish it. And all you can see is sort of things that didn't look like a transformer. I mean, you had ResNets, which have lots of this, but a ResNet would be kind of like this, but there's no self-attention component, but the MLP is there kind of in a ResNet. So a ResNet looks very much like this, except there's no, you can use layer norms in ResNets, I believe, as well. Typically, sometimes they can be batch norms. So it is kind of like a ResNet. It is kind of like they took a ResNet and they put in a self-attention block, in addition to the pre-existing MLP block, which is kind of like convolutions. And MLP would strictly speaking be convolution, 1-by-1 convolution. But I think the idea is similar in that MLP is just kind of like a, typical weights, nonlinearity weights sort of operation. But I will say, like, yeah, it's kind of interesting because a lot of work is not there, and then they give you this transformer, and then it turns out 5 years later it's not changed, even though everyone's trying to change it. So it's kind of interesting to me that it's kind of like a package, like a package, which I think is really interesting historically. And I also talked to paper authors, and they were unaware of the impact that the transformer would have at the time. So when you read this paper, actually, it's kind of unfortunate because this is like the paper that changed everything. But when people read it, it's like question marks because it reads like a pretty random machine translation paper. Like, oh, we're doing machine translation. Oh, here's a cool architecture. Okay, great, good results. Like, it doesn't sort of know what's going to happen. And so when people read it today, I think they're kind of confused. potentially. Like having, I will have some tweets at the end, but I think I would have renamed it with the benefit of hindsight of like, well, I'll get to it. Yeah. Yeah, I think that's a good question as well. Currently, I mean, I certainly don't love the autoregressive modeling approach. I think it's kind of weird to like sample a token and then commit to it. So, you know, maybe there's some ways to, some hybrids with diffusion as an example, which I think would be really cool. Or we'll find some other ways to like edit the sequences later, but still in the autoregressive framework. But I think diffusion is kind of like an up and coming modeling approach that I personally find much more appealing. When I sample text, I don't go chunk, chunk, chunk and commit. I do a draft 1 and then I do a better draft 2. And that feels like a diffusion process. So that would be my hope.
Okay, also a question.
Yeah.
So yeah, I use like the graph logic with the tips of it visualize what's happening. Would you say like this self-attention is sort of like computing like an edge weight using like the dot product on the node similarity, and then once we have the edge weight, we just like multiplied by the values, and then just forget it.
Yes. Yes, right. Yeah.
And do you think there's like a analogy between like graph neural networks and self-attention?
I find the graph neural networks kind of like a confusing term because I mean, yeah, previously there was this notion of, I kind of feel like maybe today everything is a graph neural network because the transformer is a graph neural network processor. The native representation that the transformer operates over is sets that are connected by edges in a directed way. And so that's the native representation. And then, yeah. Okay, I should go on because I still have like 30 slides.
Sorry. There's a question on Zoom. Just back to softwares. Why do you divide by root?
Oh yeah, yeah. The root D, I think, basically like if you're initializing with random weights sampled from a Gaussian, as your dimension size grows, so does your values, the variance grows, and then your softmax will just become the 1/2 vector. So it's just a way to control the variance and bring it to always be in a good range for softmax and nice diffuse distribution. Okay. So it's almost like an initialization thing. Okay. So transformers have been applied to all the other fields, and the way this was done is, in my opinion, kind of ridiculous ways, honestly, because I was a computer vision person, and you have ComNets, and they kind of make sense. So what we're doing now with bits, as an example, is you take an image and you chop it up into little squares, and then those squares literally feed into a transformer, and that's it, which is kind of ridiculous. And so, I mean, yeah. And so the transformer doesn't even, in the simplest case, like really know where these patches might come from. They are usually positionally encoded, but it has to sort of like rediscover a lot of the structure, I think, of them in some ways. And it's kind of weird to approach it that way. But it's just like the simplest baseline of just chopping up big images into small squares and feeding them in as like the individual nodes actually works fairly well. And then this is a transformer encoder. So all the patches are talking to each other throughout the entire transformer. And the number of nodes here would be sort of like 9. Also in speech recognition, you just take your MEL spectrogram and you chop it up into little slices and feed them into a transformer. So there was paper like this, but also Whisper. Whisper is a copy-paste transformer. If you saw Whisper from OpenAI, you just chop up MEL spectrogram and feed it into a transformer, and then pretend you're dealing with text, and it works very well. Decision transformer in RL, you take your states, actions, and reward that you experience in the environment, and you just pretend it's a language, and you start to model the sequences of that. And then you can use that for planning later. That works pretty well. You know, even things like AlphaFold. So we were briefly talking about molecules and how you can plug them in. So at the heart of AlphaFold computationally is also a transformer. One thing I wanted to also say about transformers is I find that they're they're super flexible, and I really enjoy that. I'll give you an example from Tesla. Like you have a ComNet that takes an image and makes predictions about the image. And then the big question is, how do you feed in extra information? And it's not always trivial. Like say I have additional information that I want to inform, that I want the outputs to be informed by. Maybe I have other sensors like radar. Maybe I have some map information or vehicle type or some audio. And the question is, how do you feed information into a ComNet? Like where do you feed it in? Do you concatenate it? Like how do you add it? At what stage? And so With the transformer, it's much easier because you just take whatever you want, you chop it up into pieces, and you feed it in with a set of what you had before. And you let the self-attention figure out how everything should communicate. And that actually apparently works. So just chop up everything and throw it into the mix is kind of like the way. And it frees neural nets from this burden of Euclidean space, where previously you had to arrange your computation to conform to the Euclidean space of 3 dimensions of how you're laying out the compute. Like the compute actually kind of happens in almost like 3D space, if you think about it. But in attention, everything is just sets. So it's a very flexible framework, and you can just like throw in stuff into your conditioning set, and everything just self-attended over. So it's quite beautiful from that perspective. Okay. So now, what exactly makes transformers so effective? I think a good example of this comes from the GPT-3 paper, which I encourage people to read. Language models are 2-shot learners. I would have probably renamed this a little bit. I would have said something like transformers are capable of in-context learning, or like meta-learning. That's kind of like what makes them really special. So basically, the setting that they're working with is, okay, I have some context, and I'm trying to, like, say, passage. This is just one example of many. I have a passage, and I'm asking questions about it. And then I'm giving, as part of the context in the prompt, I'm giving the questions and the answers. So I'm giving one example of question answer, another example of question answer, another example of question answer, and so on. And this becomes, oh yeah, people are going to have to leave soon. Huh? Okay, is this really important? Let me think. Okay, so what's really interesting is basically like, with more examples given in the context, the accuracy improves. And so what that hints at is that the transformer is able to somehow learn in the activations without doing any gradient descent in a typical fine-tuning fashion. So if you fine-tune, you have to give an example and the answer, and you do fine-tuning using gradient descent. But it looks like the transformer internally in its weights is doing something that looks like potentially gradient descent, some kind of a meta-learning in the weights of the transformer as it is reading the prompt. And so in this paper, they go into, okay, distinguishing this outer loop with stochastic gradient descent and this inner loop of the in-context learning. So the inner loop is as the transformer is sort of like reading the sequence almost, and the outer loop is the training by gradient descent. So basically, there's some training happening in the activations of the transformer as it is consuming a sequence that maybe very much looks like gradient descent. And so there's some recent papers that kind of hint at this and study it. And so as an example, in this paper here, they propose something called the raw operator. And they argue that the raw operator is implemented by a transformer. And then they show that you can implement things like ridge regression on top of a raw operator. And so this is kind of giving, there are papers hinting that maybe there is something that looks like gradient-based learning inside the activations of the transformer. And I think this is not impossible to think through, because what is gradient-based learning? Forward pass, backward pass, and then update. Well, that looks like a ResNet, right? Because you're just changing, you're adding to the weights. So you start with initial random set of weights, forward pass, backward pass, and update your weights. And then forward pass, backward pass, update weights. It looks like a ResNet. Transformers are ResNet. So much more hand wavy, but basically some papers trying to hint at why that could be potentially possible. And then I have a bunch of tweets I just copy pasted here in the end. This was kind of like meant for general consumption, so they're a bit more high level and hypey a little bit. But I'm talking about why this architecture is so interesting and why potentially it became so popular. And I think it simultaneously optimizes 3 properties that I think are very desirable. Number one, the transformer is very expressive in the forward pass. It's sort of like is able to implement very interesting functions, potentially functions that can even like do meta learning. Number two, it is very optimizable thanks to things like residual connections, layer norms, and so on. And number three, it's extremely efficient. This is not always appreciated, but the transformer, if you look at the computational graph, is a shallow, wide network, which is perfect to take advantage of the parallelism of GPUs. So I think the transformer was designed very deliberately to run efficiently on GPUs. There's previous work like neural GPU that I really enjoy as well, which is really just like how do we design neural nets that are efficient on GPUs, and thinking backwards from the constraints of the hardware, which I think is a very interesting way to think about it. Oh yeah, so here I'm saying I probably would have called the transformer a general purpose efficient optimizable computer instead of attention is all you need. Like that's what I would have maybe in hindsight called that paper. It's proposing a model that is very general purpose, so forward pass is expressive. It's very efficient in terms of GPU usage, and it's easily optimizable by gradient descent, and trains very nicely. Then I have some other hype tweets here. Anyway, so you can read them later, but I think this one's maybe interesting. So If previous neural nets are special purpose computers designed for a specific task, GPT is a general purpose computer reconfigurable at runtime to run natural language programs. So the programs are given as prompts, and then GPT runs the program by completing the document. So I really like these analogies personally to computer. It's just like a powerful computer, and it's optimizable by gradient descent. I don't know. Okay, yeah, that's it. You can read the tweets later, but for now, just thank you. I'll just leave this up. Maybe. So sorry, I just found this tweet. So turns out that if you scale up the training set and use a powerful enough neural net like a transformer, the network becomes a kind of general purpose computer over text. So I think that's a kind of like nice way to look at it. And instead of performing a single text sequence, you can design the sequence in the prompt. And because the transformer is both powerful, but also is trained on large enough, very hard data set, it kind of becomes this general purpose text computer. And so I think that's kind of interesting way to look at it. Yeah.
You have 3 points about.
Yeah.
So I guess like for me, I learned about neural networks first. And then you get all function. You have an RNN.
Yes. Yes.
So, and I sort of developed like a transformer. I mostly like already with that
yes.
Sort of thing, but now we see kind of ideas that like you think there's really metal or creative. And I guess my question is how much do you think it's like is really like most of it? You know, like is it really because it's mostly more efficient, or do you think is there any sort of like opinion you have that like maybe transformers have like a specific inductive bias towards the beautiful ingredient?
Yeah. So I think
Yeah.
there's a bit of that. Yeah. So I would say RNNs, like in principle, yes, they can implement arbitrary programs. I think it's kind of like a useless statement to some extent because they are not. They're probably. I'm not sure that they're probably expressive because in the sense of like power, in that they can implement these arbitrary functions, but they're not optimizable, and they're certainly not efficient because they are serial computing devices. So I think so. If you look at it as a compute graph, RNNs are very long, thin compute graph. Like if you stretched out the neurons and you look, like take all the individual neurons and their connectivity and stretch them out and try to visualize them, RNNs would be like a very long graph, and it's bad. And it's bad also for optimizability because I don't exactly know why, but just the rough intuition is when you're backpropagating, you don't want to make too many steps. And so transformers are a shallow wide graph. And so from supervision to inputs is a very small number of hops. And it's along residual pathways, which make gradients flow very easily. And there's all these layer norms to control the gradient, the scales of all of those activations. And so there's not too many hops, and you're going from supervision to input very quickly, and just flows through the graph. So, and it can all be done in parallel. So you don't need to do this encoder decoder RNNs. You have to go from first word, then second word, then third word. But here in Transformer, every single word was processed completely sort of in parallel, which is kind of so I think all of these are really important because all of these are really important. And I think number 3 is less talked about, but extremely important because in deep learning, scale matters. And so the size of the network that you can train gives you is extremely important. And so if it's efficient on the current hardware, then you can make it bigger.
You mentioned that you're dealing with like multiple modalities of data, you sort of feed it all together. How does that How does that actually work? Do you like leave the different data as different tokens, or is it
No. So you take your images and you apparently chop them up into patches. So there's the first 1,000 tokens or whatever. And now I have a special. So radar could be also. Well, I don't actually know the native representation of radar. So, but you could you just need to chop it up and enter it, and then you have to encode it somehow. Like the transformer needs to know that they're coming from radar. So you create a special. You have some kind of a special token that you like these radar tokens are like slightly different in the representation, and it's learnable by gradient descent. And like vehicle information would also come in with a special embedding token that can be learned.
Have you learned those like orally?
But you don't. It's all just a set.
And there's no the positional encoding, you know, which and but
yeah, it's all just a set. But you can positionally encode these sets if you want. So, but positional encoding means you can hardwire, for example, the coordinates, like using sinusoids and cosines. You can hardwire that. But it's better if you don't hardwire the position. It's just a vector that is always hanging out at this location. Whatever content is there just adds on it, and this vector is trainable by background. That's how you do it. Yeah.
I don't really like this solution. I think they're kind of delicate. Like they seem to work, but it seems like there's sometimes hard situations where you want to include some structure of the relationship or the station or whatever else. Do you have any ideas for how you might do something better?
I'm not sure if I understand the question. So I mean, the positional encoders, like they're actually like not. They have so they have very little inductive bias or something like that. They're just vectors hanging out in location always, and you're trying to help the network in some way. And I think the intuition is good, but like if you have enough data, usually trying to mess with it is like a bad thing. Like trying to enter knowledge when you have enough knowledge in the data set itself is not usually productive. So it like really depends on what scale you are. If you have infinity data, then you actually want to encode less and less. That turns out to work better. And if you have very little data, then actually you do want to encode some biases. And maybe if you have a much smaller data set, then maybe convolutions are a good idea because you actually have this bias coming from little filters. And so, but I think, so the transformer is extremely general, but there are ways to mess with the encodings to put in more structure. Like you could, for example, encode sinuses and cosines and fix it. Or you could actually go to the attention mechanism and say, okay, if my image is chopped up into patches, this patch can only communicate to its neighborhood. And you just do that in the attention matrix, just mask out whatever you don't want to communicate. And so people really play with this because the full attention is inefficient. So they will intersperse, for example, layers that only communicate in little patches, and then layers that communicate globally. And they will sort of do all kinds of tricks like that. So you can slowly bring in more inductive bias. You would do it. But the inductive biases are sort of like, they're factored out from the core transformer, and they are factored out in the connectivity of the nodes, and they are factored out in the positional encodings, and you can mess with this per application.
How you could try to so then I think there's probably like a usually has that. How do you imagine it resolved?
So there's probably about 200 papers on this now, if not more. They're kind of hard to keep track of. Honestly, like my Safari browser, which is, it's on my computer, like 200 open tabs. Yes, I'm not even sure if I want to like pick my favorite, honestly.
Yeah, obviously there was this very interesting talk from US this year. And you can think of a transformer as like a CPU. I think first there's this fixed size instruction that could like 4,000 token done. And then like now when you get into the CPU, what you have is like you store variables, you have memory. So it's like if I want to interpret a program with the CPU, I just like do it multiple times. So maybe like you can use a transformer like that to get there.
The other one that I actually like even more is potentially keep the context length fixed, but allow the network to somehow use a scratch pad. Okay. And so the way this works is you will teach the transformer somehow via examples in the prompt that, hey, you actually have a scratch pad. Hey, basically, you can't remember too much. Your context line is finite, but you can use a scratch pad, and you do that by emitting a start scratch pad, and then writing whatever you want to remember, and then end scratch pad, and then you continue with whatever you want. And then later, when it's decoding, you actually like have special logic that when you detect start scratch pad, you will sort of like save whatever it puts in there in like external thing and allow it to attend over it. So basically, you can teach the transformer just dynamically because it's so meta-learned. You can teach it dynamically to use other gizmos and gadgets and allow it to expand its memory that way, if that makes sense. It's just like human learning to use a notepad, right? You don't have to keep it in your brain. So keeping things in your brain is kind of like the context line for the transformer. But maybe we can just give it a notebook, and then it can query the notebook and read from it and write to it.
Maybe you can use a transformer to query another transformer.
I'm just saying that we didn't chat GPT.
in a way, but they're clearly going to this with some sort of memory. It feels like the idea that track that presently.
I don't know if I detected that. I kind of feel like, did you feel like there was more than just a long prompt that's unfolding?
Yeah, it feels like sometimes you forget.
I didn't try extensively, but I did see a forgetting event, and I kind of felt like the block size was just moved. Maybe I'm wrong. I don't actually know about the internals of ChatGPT.
Yeah. Two online questions. So one question is, what do you think about architectures like
S4?
S4?
Sorry, I don't know S4. Okay. Which one is S4?
The second question, this one's a personal question. What are you going to work on next?
I mean, so right now I'm working on things like NanoGPT. Where's NanoGPT? I mean, I'm going basically slightly from computer vision and like kind of like computer vision based products to a little bit in the language domain. Where's ChatGPT? Okay, NanoGPT. So originally I had MinGPT, which I rewrote to NanoGPT, and I'm working on this. I'm trying to reproduce GPTs, and I mean, I think something like ChatGPT, I think incrementally improved in a product fashion would be extremely interesting, and I think a lot of people feel it, and that's why it went so wide. So I think there's something like a Google +++ to build that I think is really interesting.
So we give our speaker a round of applause.